enough caffeine and you got your pencil sharpened, ready to take some notes. Our next speaker is by Dave Zilkoski. He's the former director of the National Geodetic Survey. He's been at this for many years, although he looks so young, though. I still don't understand that. He's going to be talking about guidelines for establishing GPS-derived ellipsoidal heights. And he's going to reference a paper that he authored, the famous NGS Report 58. Take it away, Dave.
Thanks, Roy. Yeah, there's two sections to this that I've been asked to give a talk on. One is ellipsoid heights, GPS-derived ellipsoid heights, and then ultimately what you really need is GPS-derived orthometric heights. So I titled this both ellipsoid and orthometric heights. And this first hour and a half of what we talk about will be about ellipsoid heights, and then the second hour and a half will be talking about orthometric heights. And then tomorrow you're going to see and hear a lot about the RTNs and the RTKs, observations by Bill and others. But today we're going to just focus on getting heights, because you really need to understand, what GPS gives you and what your RTK, RTNs are really giving you. It's very, very important that the ellipsoid height is a very useful value, but it's the orthometric height that you ultimately need. So we're going to spend a little bit of time on that. And as Roy mentioned, NGS 58 deals with ellipsoid heights. NGS 59 deals with the orthometric heights. My understanding is NGS also, ultimately will be trying to create just one document. And this is something that I've talked to Roy about and others about coming up with best practices for establishing GPS-derived orthometric heights. And that could be from static surveys or from real-time networks. I think that's something that's very, very important and needs to be really addressed. And this is where the users come in, because you're doing the work, and so you have to be a collaboration. I've been working, as Roy said, I've been working on with GPS and heights for a long time, and I started doing some work in Louisiana back in the early 80s, and dealing with the subsidence issues and heights along the levees. So a lot of my slides that you're seeing today were created by myself when I was working for NGS, but other people throughout NGS, and so it's difficult now to kind of describe which ones belong to which person. So I kind of put this slide in here to cover, everybody that I think has contributed. And if I miss someone through NGS, ultimately we can add their names eventually, or we can drop them all and just say NGS provided some of those, but we'll deal with that. But I don't want to get anybody upset. So topics we're going to discuss is you have to review types of heights and their accuracies to understand just what you're getting when you do a GPS-derived orthometric height. We'll talk about guidelines to reduce them, and then 58, talk about the 59, and then we're going to go through what, in my opinion, why the readjustment's necessary that Renee mentioned in 2022, and ultimately it's going to make everybody's life a lot easier, although GPS basically is really eliminating the need to do large network leveling projects. Most people aren't doing long level lines for control anymore. They're using GPS in the geoid model. And in 2022, I believe that probably will be totally replaced. Does that mean you're never going to have to level? No. You're going to still level. You're going to still need some very, very accurate relative differences over very short lines. So leveling's never going to go away, in my opinion. You're always going to need it. But you won't be running 50-kilometer level lines. And there's still some states that are doing some of that. You got Florida, you got Minnesota, Wisconsin, Mississippi just did some. And so they're still necessary now. One of the things I'm going to spend some time on is detecting errors and reducing and eliminating. I mean, that's the whole thing about guidelines. Guidelines are developed to either detect that you got a problem, or you already know you got a problem, so you want to reduce the effect of that, or you can eliminate it. And that's what I spent a lot of time before we put out 58 and 59. I spent a lot of time trying to look at what is causing the problem. If I collect data, what are my potential pitfalls, and what do I have to do to try to mitigate those pitfalls? And when I first started doing the guidelines, because I worked for NGS and federal government, if you put out guidelines, you got to make sure they're right. You got to stand behind them. So if you're wrong, then someone gets sued, and it's very difficult to sue the federal government. But they said back to the federal government, they said, I followed their guidelines, so I got to be right. So that means when you put out something for the federal government that says it's guidelines, you have to really check them out. And when I did it, I involved a lot of locals. I developed the guidelines and said, okay, this is based on my best knowledge. And then I had a lot of the users come to me and say, you know, I can get better than that. I don't need to do that. So each time I did that, I learned a little bit more about what they were doing. And then I incorporated some of those procedures in the guidelines. But at the same time, I would also show them sometimes why they were doing it, that they were getting precision but not accuracy. And so that's something I'll talk a little bit about. So as I said, you got to know what types of heights you're dealing with, because there are 3 different types of heights that we're going to look at. How they're defined and related, you saw a slide earlier, and I'll spend a little bit of time on it, but we're not going to spend a lot of time. Now, we used to teach a 2-day workshop and seminar on GPS-derived ellipsoid and orthometric height. So we're summarizing this in basically 3 hours. So you got to understand that this is going to give you some information, the very basics of the guidelines, but also give you the ability to maybe ask questions if you got a problem, and that's part of what we'll get to. And then how accurate can you determine? And you'll hear some of the new stuff that's coming out when we talk about with Jerry and Mark, where they talk about the geoid and opus. All right, ellipsoid heights. I think everybody understands that's what you get out of GPS now. But when you're done with it, you collect this data, you put it in the software. A lot of times what people are coming out with is they're giving them orthometric heights. So if you don't understand that just GPS gives you the ellipsoid height, then something else has to be applied to it, the geoid model, then you're getting that result without understanding all the parameters going into it. And there are a lot of people that said, well, I put it into my machine, I ran it, collected the data, you plug it into a computer program, you apply some geoid model, and it gives you an orthometric height. And in many cases, in the beginning, they were just calling it WGS 84. But it gave you an orthometric height. So you have to know some of that. So we'd like to spend some time, and in this workshop, you're going to hear more time about the geoid model, which is probably one of the most critical parts now of doing the GPS-derived orthometric height. In the beginning, you worried about, well, how can I get an accurate ellipsoid height? Well, the procedures really stand out. Getting better, or getting more satellites up there helped. Better processing tools, better instrumentation. That all really helped and minimized the errors. But the geoid model still is that little uncertainty, because it's very difficult to really show and prove how accurate do I really know that geoid model. And especially in southern Louisiana, where you try to prove how accurate you know it is by comparing it to benchmarks, which now have subsided. But these are the critical parts of the meeting today. And then tomorrow, when you're talking about the real time, and you're talking about getting ellipsoid heights, but you ultimately got to end up with orthometric heights. So you have to throw that geoid model into it. So in this diagram here, a very simple diagram, we talk about the geoid. This is the surface that we're saying we're referencing all our heights from. All of our orthometric heights are referenced to that. And that's not something that you can just dig down and see it, a little blue line going through the country. You can't have a geoid meter to go out there and just measure it and say the geoid height's this. You have to mathematically derive it using gravity information and others. You heard Cliff talk about what they did 30, 40, 50 years ago. We're just getting better at doing it. But it's still a model, and it still has to be validated. But an orthometric height, as you can see, is measured from this geoid on the plumb line going up to the surface. That's the orthometric height. And when you get that orthometric height today, you're using leveling data. In the process, in the NAVD-80A, we took into account the fact that that's where the geoid was and where we were measuring it, we corrected the leveling observations for error sources so that you ended up with an orthometric height. And then in the NAVD8, you had to pick a type of orthometric height. So you might hear the term Helmert orthometric height, and that's the assumptions that we used the Helmert equation that's saying what's the density, average density going up that line, and it was a Helmert equation. We could have picked something different, but that's what we ended up picking. But that's what makes the NAVD88 the NAVD88, the Helmert orthometric height. So that's a key point, because in the NGV29, it wasn't a Helmert orthometric height. It was called a normal orthometric height, and they are not the same. So all these datums and references, it's important to understand that every one of them has a meaning, and as long as you stay within one system, then you're consistent. Now, the other point of this diagram is, here's the ellipsoid, and the ellipsoid height is measured from the ellipsoid up to the point. And obviously, you can see that the ellipsoid height and the orthometric height are not the same, and the difference between them is what we call the geoid height. And that's what you see on all these data sheets from NGS as this geoid height. But remember, this is modeled. And every time you get a new model, then this value from here to here and from here to here changes. Even if this value doesn't change or that surface doesn't change, when you change that geoid height. That's why it's important that you can't mix and match geoid models too. You have to be consistent. Now, in our procedures for the orthometric height, you'll see later on this afternoon, even if you have slightly different geoid models, if you follow the procedures, then you would still end up with NAVD88 heights that were pretty consistent, and then that geoid difference might drop out on your local project. But you still have to be careful. There you could compare GPS-derived NAVD88 heights, the final product, with each other, if you follow the appropriate procedures. But still, the geoid model could make a difference in some areas. Yeah, I guess I'll take questions as we're going. It's fine with me. Go ahead.
Capital H up there, orthometric height, the difference along the plumb line shows so it would be the addition of M and little a. Isn't your formula up there wrong?
No, it's correct, because the way this is the correct formula, and if you have a negative geoid height or ellipsoid, you have to apply it. But the formula is correct, yeah? And the diagram, it's always a little confusing. And the original diagram, the formula was just out of straight things coming out of DMA years ago.
But still, you should have capital H equals small h plus capital M. And then it's an algebraic addition.
No, because this is basically, n would become a negative number, and when you apply a negative number or ellipsoid, either one of them becomes negative. In other words, this is a very difficult way of trying to show that equation. You're right, but because of the equations based on where the geoid model in the original one would be above the diagram. The equation's originally written where the geoid model fits up in here, so then you would have the equation being h plus n would be there. So in other words, below it is negative. I'm not sure I'm making sense to you. In other words, if you move where this geoid model is, this is typically how it is in the US, that's why we draw it that way, and put it where it was in its original design, how they came up with the equation. The numbers were positive, so it said that it turned out to be that way. But if you include the negative sign, then you get the correct answer. Does that make sense? I'll talk to you later about it afterwards and try to explain a little bit what a diagram. So So we did guidelines, expected accuracies now a little bit. We did some guidelines with ellipsoid heights, and if you follow the guidelines and these procedures that we outline, then you can expect to get better than 2 centimeters in your ellipsoid heights. And it's better than 2 centimeters. I say that when we designed it because we wanted to be in local areas to ultimately try to get your GPS-derived orthometric heights to the 2 centimeter level. So these diagrams will give you slightly better than 2 centimeters. The geoid heights in Geoid 09, and I'll show you a couple diagrams of this later, and Jerry will talk a little bit more in detail, is relative differences is only a few millimeters in 10 kilometers. So the relative differences are very small, and the total misfit's like 1.4 centimeters squared. So if you take it in an absolute sense, it's going to be larger. All of our guidelines and procedures are always assuming that you're in a local area doing relative differences. So some of these error sources drop out. That's how you get your geoid model better than that 1.4 centimeters in a very local area. The difference in the error in the geoid over the slope is less. And that's a key, that right there is a key to how you use these procedures and try to get GPS-derived orthometric heights. You're going to see that they don't match up if you try to do it point by point, which could be an issue when you're using Opus and standing on something and you get a value there. But if you take that one value and go 2 or 3 kilometers away and take another one, the error in the geoid height difference is smaller. And that's how you're able to do better GPS-derived orthometric heights in over short areas. And I'm going to show you in this afternoon procedures to be able to remove some of that remaining tilt that may exist. And then leveling derived heights. In 1 centimeter, even third order, in 10 kilometers, even third order leveling is better than a centimeter. Now, immediately people say, well, wait a minute. In 10 kilometers, I'm allowed 1.2 centimeters of misclosure times the square root of kilometers. That's a misclosure. Okay, remember, if you follow third order specification procedures as they are written as part of the federal guidelines, when you're done, you will actually have better than about 1 centimeter in 10 kilometers. Even though your misclosure that you're allowed, section by section and over the 10 is larger, because it's the process you're going through. Misclosure is one part of it, but if you level forward and you level back, and your misclosure is within that tolerance, you're actually taking the mean value. So your individual error in one level section is now meaned, and so you are taking out and removing some of the other errors. So you can't use the misclosure. Misclosure is not a measure of accuracy. It is just one procedure. You have to follow the procedures. You have to balance sight lengths. You have to minimize the height so you don't have a lot of refraction. So when someone just goes out and says, well, I got all my forward and backward runnings and I got a very good agreement, if you didn't follow the procedure, you could still have errors. That's the importance of guidelines and procedures. So it's very clear that that only happens if you're following the federal procedures for doing it. If you try to do something different, you may be getting that. I'm not saying you're not. If you do your own little procedures, all I'm telling you is if you do the federal ones, that's what you get. And that's the whole thing about these guidelines. When I talk about these up in here, we know that they work. You might be able to do something different, and that's very good. Me personally, when I was at NGS, I would stand behind the guidelines, and if you did that and something didn't work, we can fix it. I can figure out what's going on. If you do something different, then I don't know exactly what went on. And I had someone that called me up one time, and they had a problem with their GPS network. The heights wasn't consistent, so I said, well, okay, first of all, I said, did you follow the guidelines? They said, well, no, I didn't. I said, all right, well, tell me what you did. So when they were all done, they told me a lot of stuff they did with single baselines, and they occupied things twice, but there wasn't any way of checking repeat baselines. And finally, when I got all the information, I said, I can't tell you why you got a problem. I don't know how to fix it. The person said, okay. They went back, and then I got a call from that same person about 2 months later and they said, you know, we followed the guidelines and we didn't have any problem on this project. Everything seemed to work. So even though they spent a little bit more time on the second project, it actually cost them less to do than the first project, because the first project had to go back and redo some of it to figure out where the problems were. And that's part of the design of federal guidelines. All right, so we reviewed these types of heights and their accuracy, and now we're going to talk about guidelines for detecting and reducing and eliminating these error sources. Remember, it's very, very important that the guidelines reduce, detect, and eliminate. I just got through telling you a little story about a person doing something out there and then it didn't seem to work and didn't check. And without having the appropriate procedures in place to detect or reduce, then you can't answer, did I reduce the error that I think I might have? Did I do something to detect it? And usually if you have a major problem, your data should be able to tell you that you have a major problem. And if it doesn't, then chances are you got to do some more processing of procedures. So error sources can be labeled in these three categories: random, systematic, and blunders. The guidelines and procedures always are trying to get rid of as much of the systematic errors as you can, detect all of the blunders, and get them out of there, so that you're really left with the random error, which is the small part that you can't model. That's what your goal is. And that's all guidelines do. That's all they really do. They're really in the process of saying, if you follow these procedures, I know you're going to detect these type of error sources or reduce these error sources, and clearly find those blunders. So, I've said it over and over again, they help detect, reduce. We did a lot of special projects to develop the guidelines. And we spent a lot of time designing these projects to be able to find what error sources existed. And after we identified what we thought were some of them, I talked to a lot of users. And I had a lot of users out there telling me, you know, when I first did them, they said, you tell me I gotta sit out here for 3 hours or 6 hours and over a couple days, and I don't see it. I'm doing this a lot shorter, 1 hour, and I come back the next day and I get answers to a few millimeters. What gives? And they were doing one day at 8 o'clock, they'd observe this baseline, come back at 8 o'clock the next day, and they wouldn't find a problem. Or they wouldn't repeat the baseline, they would do or loop around 2 or 3 stations and say, I occupied the station twice, which they did, but they're individual baselines. In the guidelines, you're required to occupy the baseline twice. And there's a reason for that. Just like in leveling, a forward and backward run, it takes and helps to reduce the mean value that you're going to end up with. So when you do your adjustment, you have additional data observations. So you're going to get a better value because you repeated it. Same thing with theodolites. If you remember when you took 16 positions, or if you did first order work, or you did 8 positions when you were coming down to go in the second, and you did it around a circle. All you were doing was eliminating the errors in the theodolite for around the circle. You had to take the mean. You did 16, and you got better if you did more. And as you got down to third order, maybe you did even less than that. But you still repeated it because you had to compensate. You had an error source that you had to eliminate by going around the circle. But all the guidelines that we produced there have been modified during the process when we got better equipment. When people said, you know, I think that some of these guidelines can be loosened a little bit and let's work together, and we did. So we reduced some of them down to shorter observing stands, but other times we didn't change about what you could do on different days and so forth. But we did work with the users on that. And I think now what NGS is looking at is you got 58, you got 59, you got these RT networks out there, and there's a lot of additional information. And so now, should 58 and 59 be rewritten slightly? With the advent of all the cores that you have, the NSR's 2007, a new adjustment coming with the ellipsoid heights that are spaced across the U.S.? Do you need primary control? These are all things that NGS is, in my opinion, needs to continue to look at, which I believe they are. So one of the things that I spent a lot of time on is I took data sets that I had 24-hour data sets, because I had a lot of this in the Harris-Galveston region and other parts of the country where we had computer operating station cores back before you had the thousands that you have now. So I had 24-hour data sets, and I had very, very accurate coordinates, and I was focused more on the ellipsoid heights only. But I had very, very accurate ellipsoid heights between these stations because I had 24-hour data sets for days. And so I could compute what I thought was truth within the accuracy of the data, of course. So I would do that and say, okay, this is truth. And I did that for this station at Lake Houston. This is a 23-kilometer line. But I took, basically this is 5 days, and I took all the data, processed, and got an average, and I said, well, I think that's what my height difference will be in that 23 kilometers line. And I did it and broke it up into 6-hour, this one, 6-hour segments. So I took from 0 to 6, and then 1 to 7, 2 to 8. I just did all this and just number crunched all of this data just to try to get a feel for, if I observed for 6 hours at this time, what would I get? If I observed at this time, what can I get? Now, obviously, they're all these numbers are related a little bit because they're all using some of the other data. 0 to 6, 1 to 7 is using data from 1 to 6 over. So they're related. But that was what I was looking. What I was looking for is, would I see trends? Would I see differences based on when I did the data? And then I plotted them all. And you can see that there are some that hang together, and then there's some that just jump up. And this is a centimeter right here, by the way. So that's like 1.5 centimeters. And remember, these aren't supposed to change. They're supposed to give me an answer of about that number, 5.71, because that's what I know is truth. And at this day right here, I could take a couple days of data at the same time and get a good mean value. Their difference is like 5 millimeters, but the mean is 3.1. I can come down here and take 2 days of data, okay, at the same time and get a difference of 3 millimeters, but its mean is 7.5. So the difference between here and here is over 4 centimeters. So that led me to believe that, hey, there's something about when I'm observing around the time of day. Now remember, this is older data that we had, and you got better instrumentation now, and you better more satellites and so forth. Although in most cases in here, we still had quite a bit of satellites up when we were doing this. But some of that plays that part. Some of it has to do with atmospheric conditions, multipathing going on. All of those kind of things are occurring. But the point being is that I got good precision here, but not accuracy. And this is what a couple groups were saying. They said, I see I'm getting good results. Why do you want me to have to keep repeating these baselines? I'm seeing the same number. Well, if you came back at this time, you'd get that number. If you came back at this time, you'd get that. And then their difference is 4.5. But look at the mean value. It's minus 5.5. And look what I think truth is. So we were looking at this and saying, well, you know what? If we can repeat these over a couple days, different times of the day, then I take into account some of the geometry change of the satellite, some of the multipath going on, some of the atmospheric effects, all which cause some problem of the data. And that was what we're after. Here's another one, and it's 4.2 kilometers, because now that was the other issue. I had a lot of individuals were saying, I'm only going 4 or 5 kilometers. I'm not going this 20, 30 kilometers because I'm doing a local project. And there was a mix. There were some people that wanted to do both. And I said, all right, well, we'll take a look at that. And even there, you can see that got similar type things. You got some good agreement here, and down here it gets less. The agreement, if you take the mean value between the two, they differ right here by 7 millimeters. The mean should be 1. But you can see that these agree different than here. Same thing, running averages. This is for 3-hour solutions, and this is only a 4.2 kilometer line. But there's a pattern. You can see them coming together, and then they drop down and go like this. Now here, it really jumped, and during the same time here, there was a huge atmospheric event. I believe it started raining or something on the one day, which once again gives you a problem of having large atmospheric effects on your data. But if you take the mean value of these two, okay, then you're going to get closer to what we believe is truth. And that's what we're going at. So, all right, so I got to get closer to truth. Remember, you're trying to detect, reduce, or eliminate error sources. And that's why you got to do observations and repeat and times and so forth. New technology, new procedures, using networks, they are, and this is what you got to ask yourself when you talk about real-time networks and how you're doing it. Are they detecting, reducing, and eliminating these error sources that you're doing in a static survey? Are they handling the atmospheric effects? Are they handling the geometry differences? Those are the kind of things that real-time networks should be doing and are doing, and will vary based on that. Here's another one, the 2 hours. I mean, I took these things for 6 hours, 2 hours, and I kept going down, all the way down to 30 minutes, because that's what the users kept saying I needed. And I could do that, and I could show that same station that as I went down to 2 hours, my spread increased. But the mean didn't change that much. But the spread between these two sets increased. Okay? 3 hours of data, I got a spread of 7 millimeters. Now I got a spread of 1.5 centimeters with 2 hours of data. Mean was 1 centimeter. Mean is 1.3 centimeters. So if I do these on different days and try to average them on different times of the day, I get a better chance of getting what truth is. And here's a 1 hour solution. Once again, what happened? The spread increased, but the mean stayed but 1 centimeter. So that led me to say, well, you know what? Could be error sources. That means that someone's going to observe short data sets, you might get a larger spread. But what you have to do is you got to come back on a different day at a different time of day. If you do that, then you get a better chance of getting truth. One of our projects that we did was in California, where we spent 6 to 8 hours on sites to get good ellipsoid heights and orthometric. We knew that would give us the right good values. But we took that data, because it was a project, and we broke it up. Basically, this is just 2 days of data, and we broke it up into 30-minute segments of data. And what I tried to do is do it on a different, so I'm trying to show on a different day and a different time of the day. Like here, this is day 264, and it's at time 1800 to 1830. And then 20 hours later to day 265, I took 1400 to 1430. So it's not the same day and it's not the same time, and this would give me my delta height, okay? And then I subtracted the 2 days and got a difference between the two, and I took what I thought was the true value, which was based on, like I said, all of this data. And these are the mean differences minus the truth. So this is what I ended up with. And you can see my mean difference on 2 different days, different times of the day from truth, they're all less than 2 centimeters except for this one right here. And look at it agrees the best with itself. And it's 2 different times of the day. So that's one time at the 2000. This is 20 hours later, different time of the day. And you can see that they only differ by a millimeter, but the truth, they differ by 3.3 centimeters. So here's a rule. If you follow it, just like I said, you're still going to be out 3 centimeters. That's why you need a network. So remember, you repeat the baseline on a different day, different time of the day, and this is 30 minutes of data, by the way, and the baseline length is a little over 12 kilometers. It's a little bit longer than you really want, but here you didn't get your check, although it's still 3 centimeters is not that large, but still, you didn't get your check. If you put it in a network, if you put that in a network, then you're going to come to these stations from different directions, other sites, and that 3 centimeters ought to pop up and tell you, hey, there's something wrong with that, and then you go back and re-observe. That's why having a network is so important. And this line is greater than 10 kilometers. One of the reasons we found this consistently in a lot of our data, that over 10 kilometers, we would have some issues with some of the data, so that we would look and say, well, what's the best way of processing? But under 10 kilometers, we had less of a problem of this occurring. So you look in the guidelines, and they say you should keep if you're going to do short sessions, you should keep those baselines under 10 kilometers. That's part of the reason we did that, is because we were finding too many of them. There was something going on, and we couldn't model it properly. And we did it with, this is INSA free. We also did it with L1 solutions. We did a lot with all these different values, because there were a lot of people saying, well, L1 solution would give you a better answer in some of these cases. And so we did all of those kind of things. And in this case, it did not do anything. Point being, though, here's where if you follow the guidelines on an individual baseline, different time of the day, different day, the guidelines say you ought to be close to truth. Well, in this case, you're not. You're 3 centimeters. You're supposed to be better than that. But the guideline also says you got to connect these stations with each other, and you have to be able to tie into control so that you're able to check and make sure you have this, which I'll show you a little bit later. So this is based on the guidelines, what we were looking at. You must repeat the baselines at different days and at different times of the day. Very, very important, very critical. You got to reobserve baselines that disagree by 2 centimeters. If you're trying to get something better than a couple centimeters, one of the guidelines would say, if you really want that, if you don't get that check, if you do it on different days and you still don't get that check, then you got to reobserve it. Now remember, in this case I gave you before, we actually did it on different days. I did get a check. When you put it into your adjustment, you're going to find something large there, and there you should probably reobserve too. You got to fix integers. This was something that on short baselines, that if you can't fix an integer, there's usually some kind of problem. And this is back when people were doing float solutions, and now things are so automated for the most part. Almost everything's fixed on these short baselines. But if you can't fix an integer, then you got a problem with the data. And stations must be connected to at least 2 nearest neighbors. Remember, I had that one that checked with itself but didn't check with truth. If you got lines coming in to those same 2 stations, and in a network adjustment, then on that baseline, you're going to get a large residual on one of those vectors. And it's going to tell you which one doesn't seem to be consistent with the neighbors. That'll give you an indication of what you should reobserve, and then you could go reobserve it. Many times people just say, well, the adjustment told me it, and I got at least one baseline there, and I'm good enough. That's up to you. I think in terms of the guidelines and procedures and one line, 30 minutes, you try to do it. But there are cases where, it's out in a remote area and you can't get back there again. But at least then you have a look at what you think is the estimate from both of those baselines coming from different. But if you don't have this connection to the station, you'll never see that. You'll never see that one set of observations that agreed with itself but was wrong. This is equivalent to leveling spurs, if you will. You level down a line, and if you make a mistake going forward and back, you don't see it until you connect that end of that spur to something else that says, hey, I got a blunder. And this can happen. You can do this pretty easily with, putting little 2 centimeter plugs or more on your benchmark and then forgetting to add it the second time around, or putting it wrong, inverting. I mean, there's all ways you can do it leveling, but same idea. All right. Now, I'm going through this relatively quickly because, like I said, we spent a lot of time in a workshop of a one-day workshop and two-day workshop that used to teach on this. So I'm just trying to give you an idea of why some of this stuff is important and how they detect and reduce, which leads up to the guideline, which I've already basically summarized in some of the discussions that we've already had and what I've emphasized about detecting and reducing these error sources. But I will go through the guidelines and explain a little bit more about what that really means and then some more about why it's important. So these are the guidelines. They are available on the web from NGS, and you can download them. And I think it's in a PDF and form now, but it's easily attainable. Although I'm not sure they're easy to find on the website, but they're easily attainable because I had a hard time trying to find them myself. But they're out there. I know they're out there because I got them not too long ago. And they're standards for 2 and 5 centimeters. But all right. So what's the concept of the guidelines? Some of this is nowadays that you have cores so dense and you have your, what we call the cores in the FBN networks in this primary base of 40 kilometers. There's a lot of states that have all the way down that primary base already in place. If you looked at the the new readjustment of the spatial references 2007, you look at that, there's a lot of benchmarks that have accurate ellipsoid heights now across the nation. There's a lot of them. Are they at the 40 kilometer space? And in many places, yeah, they are. And so those coordinates are accurate. And so I'm going to describe what it means for the control station down to primary. But in many cases, they're already there. So you don't need to really do that. All you need to worry about is your secondary and your local stations. That was the intent of what NGS was doing when they were trying to work with the states to put this in a little bit denser. Ultimately, the cores, in years to come will be what you got as your primary network. That's what it's going to be. It's what it's going to grow to. And you're going to use these tools like Opus that Mark will talk about later. But in the meantime, that's not what you have. And you have to do something a little bit different. And in the Gulf Coast, many of these stations that are at that 40 kilometer are no longer valid. So you don't have it in some places. Some other places you do. But the Gulf Coast, clearly from Texas going around to Louisiana into southern Mississippi and probably southern Alabama and parts of Florida, as Roy mentioned in his presentation, or Renee showed it, that Gulf Coast, that whole area has got some issues. And so you need to think about this primary base in those areas. Cores, I think the cores network that you have and how it's been there is probably sufficient to bring you that control. You could come off of those cores and the way they validate them, the way they're checking them today, you can trust those cores. Or, obviously you got to validate that they're good, but NGS is already putting that out there for you. All you got to do is make sure that you look at it. So I'm going to talk a little bit about what this means. Now the primary base stations, now the cores are obvious. They're just cores out there running 24/7. But the primary base stations, this is what the guideline says. 5-hour sessions, 3 days. And this is what they did when they were doing this HARNS, the High Accuracy Reference Networks, the FBN, CBN surveys, all coming under slightly different names. New statewide GPS reobservations. When they started doing that, they started getting to the 5-hour, 3 session. So that you really knew that you had accurate latitude, longitude, and ellipsoid height. Spacing couldn't exceed 40 kilometers, and some of that, was just looking at how, at the time, if I stayed at 40 kilometers, I did 6 sessions, how well could I repeat myself and take care of all the different atmospheric effects that I was going to worry about? That's where that came from. So those are things that they're looking at now and saying, well, maybe 40 kilometers is, maybe I don't have to worry about that anymore. Maybe it can be longer if I need to be. That's something that someone needs to look at, and I think there's some studies that NGS has done that would also support that. Now, each one of these primary base stations needs to be connected to its nearest neighbor. So when you got a primary base station and you go to your next one, it's 40 kilometers away, you need a direct connection. You know, you need to be occupying them at the same time. I can't emphasize that enough, and I know there's a many concept out there that you go out there and you set on this site and then you stay there for a long time, then you go to the next site, you stay there, and because I have a relationship between that station and that one, and I know the point positioning, relative position from the datum to those points, that it should be good enough. And if you're staying there for 24 hours, yeah, you're right. But remember, you're trying to decrease this thing down to 5 hours now. Now, then, you got some other issues. A lot of things can happen in that other part of the day, the other 19 hours of the day. So when you talk about saying that there's no, you know, from a 24-hour solution, repeating it, you get that grid agreement, and you will, then when you take just 5 hours of that data over 3 days, you may get some inconsistencies. So you want that relative difference accurate. Because remember, when we're done building this network, we're going to have these stations across the county, wherever you are, or your state. And you got to make sure you don't have any kind of tilt to it, any kind of long wavelength error to it. You got to make sure that the one station next to the other is really good to a few centimeters, because you're going to want to fill in between it. The only way, without taking real long sessions, the only way to do it, the way I found at least, was doing it this way. Once again, these are guidelines that the government's going to stand behind. You do that, they say it works. Can you do it a slightly different way and it works sometimes? Yeah, probably will. I can't tell you what that is though. Secondary base stations. Now this is 30 minutes but 2 days, different times of the day. What's key here is the secondary base stations, they really were designed to someone say, well, you know what? I don't need this one area in between my 40 kilometer and my primary that I have there. I don't really need a lot of information right now, a lot of control. But I do need it lower than that. So to bridge down to that, you use these secondary stations. You say, okay, I'm going to put these in, and that'll give me my bridge to the next lower level. And I'm going to show a diagram that explains it a little bit more. But that's what it did. It was bridging the gap between that primary and really where you wanted to be. Because you couldn't do it all at once, and in some cases, you didn't even need it in some of those other areas. And the spacing cannot exceed 15 kilometers. We said, remember, and you don't want to try to go over 10 kilometers because you're trying to eliminate those error sources in the height difference based on the satellite information. But they allowed this to go 15 because we said, if you can get that repeatability and you create this network, then we'll know that there's an issue at a certain site or not. And once again, all base stations must be connected to its two nearest neighbors. You're going to hear that over and over again. That's the whole key to it. It's knowing relative to each other that I have this value. This is when you're putting in control, just like you always did in every control project. You're worried about getting that relative accuracy to your nearest neighbor. That hasn't changed, even from classical science. You're always worried about that relative difference, because that's really where you do the work. When someone's going to use this data to put in a bridge or put in a road or do something, they're going to go from one of these controls to the other. And they need to know that to a certain accuracy. And doing that allowed you to get to that. Local network stations, so there's 3, primary, secondary, and local. These are the sites that people say, well, this is what I really am going to deal with now. Once again, we said 30 minutes of data, 2 days, different times of the day. Because we did a lot of studies and we said, you know, if I use 30 minutes of really good data, and I'm going to put good data in quotes, good, because sometimes I'm not sure what that is, but good data, found that if you really had that, it doesn't make any difference. You had 30 minutes or you had an hour or you had 3 hours. when you did it on these 2 different days, different times, when you mean the values, you got close to truth. And if you didn't get truth, or you did get truth and you just had precision, or you got precision but not accuracy, then the network would take care of it and you'd find it. So the spacing had to be less than 10 kilometers, once again, because we're saying this is where the local, when you start getting down and you're really putting these stations in, someone's going to try to probably level between them. They're going to try to do some project and put a road in between these two. So you got to make sure that you know that connection better than that couple centimeters. And remember, you're only taking 30 minutes of data. So you're really trying to push the envelope of saying, I'm going to take this short amount of data on this day, and I'm going to hope that all my atmospheric conditions, all my atmospheric conditions, all my geometry conditions, all my weather conditions, and the multi-band conditions are going to be averaged out or eliminated. That's what you're hoping. And in some cases, you are just hoping that. And they got to be connected to nearest neighbors. Once again, emphasize that. So I want to make a note about this because I kept talking about 30 minutes. In order to obtain 30 minutes of good, valid data, the user should occupy the station at least 45 minutes. Now, when we did these guidelines, I involved a lot of local users, a lot of local surveyors. And they kept pushing back on me. You shouldn't tell me that I got to use 45 minutes a day, because I was in the beginning was saying, well, hey, if it's me, I'd use 45 minutes to an hour because of just logistics. So I said, fine. I could show that I could get good results with the 30. But I put that caveat to everybody saying, if you do the guidelines the way we said and you follow the networks, then you'll find out when it doesn't work and where it doesn't work. So we went down to 30, but I still tell everybody, you know, in 30 minutes, you may not get 30 minutes of good data. Although I'm not, you know, maybe you don't even need all 30 minutes of data. I've been looking at some of this RTK data and the networks, using networks, and I'm going to show you something tomorrow tonight, or after in the second session. I'm going to show you some results from a network that was done out west that just pretty amazing results. And it's only 30 seconds of data and repeating it and giving it. Although I'll also show you where it didn't get great results. So it's a mixed bag. So I haven't figured out exactly with the real-time networks just what are the best procedures yet. Repeatability obviously is. But I'll show you this afternoon some good parts of that and some parts that I'd be a little bit leery about. But, I mean, it's definitely working. So now, here's this project I want to describe it. So I can describe the control, the primary control, the secondary local. These are primary control points, okay? You got 4. These sites would be like your cores. They're out there. And then you got to have the primary. You say, well, I'm dealing with this area, so this is where I want to be. So now I put in this, say, these are the 4 stations I have there, so I'm going to occupy them. So I'm going to connect. That's what you mean. I'm going to occupy these sites so I can have traceability. Traceability between here and here goes through this. And I know this difference, this, and this. Do the same thing on those. That gives me traceability back to what I'm saying I know very, very well. And then you connect there. So that gives you your connection to from this around to there. That would give you a nice network, because remember, you are trying to make sure that if I have some systematic effect in my observations, I'll be able to see it with these cores. Because the cores I say I know much better than anything else. So if I can't take these observations and get close to what I should get, going from here to here to here, then I know that there's something wrong with my observation. Even though I may repeat myself. Remember, I showed you an example where I repeated myself, but I was off. So you're going to repeat these baselines 3 times. And if you can't check between here and here, then either that primary or the course information is bad, or inconsistent. It may be very accurate in truth, but you may be doing something that make you inconsistent with the network, which is usually typically what happens when people can't get that check. But that's why we say the primary station's like that. Now, in this design, this is what you would do for secondary base stations. So you can say, I'm going to fill it in. That's all the secondary base station does. I'm just filling it in a little bit because it's a big area. So these are all the secondary. And then you say, you know what? I need to connect them. And I need a connection to the primary base stations. Once again, I'm going to be able to go from here to here to here, and I better get what this tells me. I already got what I think is truth here, and if I can't get it that way, then I know, even though I might get checks here, 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 and here. Now, I did a lot of leveling data analysis, and I'm telling you what, a lot of leveling, you could have great misclosures here, 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 and here. By the time you check in there, you could be out because you have some small systematic effect that you were doing in your procedure or processing. So that's where some of these guidelines also came. You know, it's like I'm thinking this just like a level network, and saying, hey, if you can't detect this error or reduce it individually with the plugin, then you need to have this network. Then you do the same connection going back on the other side, so you have that connection. And then a lot of times people do that connection there, so you can just ensure that you have, because you want to make sure that you're tight, because remember, these are maybe a little bit further than the 10 kilometers, but you're still trying to do 30 minutes of data. And then you're going to say, well, now I want to put my local control in. And this is where I'm interested in putting it, up in here. I didn't need it down lower. So once again, I put a connection here. I didn't bother up here because I'm going to get that connection in a second. But you can see, this is where I want my local control. And now I do the same thing. I try to connect to nearest neighbors, try to connect to the other control, so I have traceability coming back once again between all of these now. And then I would probably do a connection there. Now, what you have, look at what you have. You have a network. And so, if I find that same one I gave you where I had a baseline on one day and I came back the next day and I checked with itself, but I was out 3.5 centimeters. If it's inside here, I should find it. The network should tell me. It's like in this loop or this one here, somewhere it's not going to agree with its neighbor, and then the residuals are going to pop out. That's the importance of having networks. Now, remember, we're talking about control surveys, so that if you did that and you put this in an area and then you want to go in and do some local surveys, now you have very, very accurate ellipsoid heights. We still haven't got the orthometric heights yet, but you've got ellipsoid heights. Without that information, you don't have that. So that's why we talk about primary stations, secondary stations, and then the local surveys stations. And like I said, today, the primary stations and many of these, even secondary, they're already in existence. They're there. They're in a lot of the networks. So you already have that. So you don't have to redo that as long as you can say it's in the network. 5 minutes? Okay. You don't have to redo that if you already can say it's in the network. I mean, in many cases in Southern Louisiana, you may not have that, so you may have to establish those. Even though you have a lot of the cores, you may still need to establish those. But then you have to figure out what's best. Should I just do some long sessions and establish primary base stations close again and do my project? With a lot of cores that you have in your network? That's what I'd probably do. This is just a summary of all this. In the guidelines themselves, it has all that thing that I talked about in a tabular form, talking about what you needed to do, highlighted and summarized in the document itself. That's all. So, to kind of finish up this part of the presentation just before we break for lunch, the basic concept of the guidelines, okay? They're three-dimensional networks connected to local networks better than 5 centimeters. Remember, I'm talking about 2 centimeters, but once you do all this locally, when you go across from one area to the next, we're really only saying that you know those to 5 centimeters. I think it's better than that. But back when we're guaranteeing things, we're saying it's only that. Nowadays, with all the cores that you have and all the way they did the NSRS now, you have that better. So that's something that we should think about what that really means now. Is it better than that? It's not changed yet in the guidelines. So I'm not saying that it is. I'm just saying I think that's something we should look at, and I think we're going to find is better. Stations within a 3-dimensional network good to 2 centimeters. So the concept saying is when you're using all your cores data in one area, when you use cores in the next data, or if you use your primary base in one area and your primary base in the second, I'm saying I know those local stations to 5 centimeters from here to here. Each one of the local stations I know to 2 centimeters. 2 centimeters between here and here, 5. That's what the guidelines are telling you you're doing that way. Could be better, but that's what they're telling them. And stations established following the guidelines are published to centimeters. You saw that by Renee. And here's what I meant. See here, local accuracy could be 2 centimeters, local accuracy 2 centimeters, but from here to here, known it to 5 centimeters. Now, once again, now that they have the NSRS and they're redoing a lot of, you may find that this is even better than that. But that's what the guidelines tell you, what you can do. And that's what it means by, the guideline means by that. So, why follow them? Repeat baseline rule helps to detect, reduce, and eliminate error sources. Network approach helps to detect, reduce errors that may be introduced due to using short observing sessions. And if you get anything out of this thing, what I said, because I must have said it 1,000 times. Guidelines help you detect, reduce, and eliminate error sources. Networks also help to detect and reduce. You're trying to take something that in a very small area with short observing sessions that have atmospheric effects and positional effects, all trying to eliminate those using 30 minutes of data on a couple different days. The network helps to ensure that you haven't introduced some kind of tilt to it in your process and your observations. That's why the network's critical for doing it to this accuracy. And I think this would probably be a good time to break because we've got another half hour right afterwards, and then I'll go into the orthometric heights after that.